Now that you're done with the homework, let's talk about it. We're in section 3.3 doing problems on page 301. First, let's look at problem 107. We're supposed to calculate something, what is this, S, for some helix. All right, so what is this, arc length? Probably. Now to calculate arc length, the better way to do it is probably just to follow the original formula. In my case, I follow the formula that's worked out for on page 285. The problem is to figure out that formula, you got to figure out what each number is in the formula. Okay, like for example, I had to figure out what R is, and then I messed up here, but I kept going. And then we rewrite R of t exactly like they want it in the format of the formula. So then I identify what R is, and well, the one up here is wrong. Okay, so I identify what R is, what N is, and then what H is, plug it in, and finally came out with 2 pi, which is now I don't think following the original arc length formula would have been an inch more difficult than what I did. So, but either way, okay, the answer is 2 pi. You go around once of the helix. So next, let's look at the next thing, which is problem 101, which we have, we're supposed to calculate, I guess this must be the curvature, the arc length. Well, you just plug in the formula as you're told. See? So that's what I did. I calculate R prime. The formula involves R prime, and you do some kind of Pythagoras theorem in 3D. And the problem is now you have to do the integration, which I'm not about to work on that. So I plugged it into the definite integral calculator, and it gave me this answer, which is not as neat as the answer in the back, but the same thing if you do a small amount of math. So that's that. Now next, let's look at problem 127, where the book doesn't say where t starts, so we'll choose t start as 0, because that is for the integration. You have to start somewhere for the definite integration. And having said that, apparently that makes it a very short problem. So if t start is 0, we figure out what R prime is, which is a simple matter, right? It's actually constant. No variables, that is. And then we do the quick integration, and then this is figuring out the R of S, the parametrization or something like that. Okay, so you're giving R of t, and you're supposed to plug t in and put S in instead. So you do that, and that's the quick answer. So that is 127. And next, we are going to look at problem 131. Now, problem 131 tells you to find the maximum curvature kappa for the graph y equal to 1 over x. Now, we all know what that looks like, okay? Y equal to 1 over x is this thing. It goes like that, right? And then the exact same thing down here. Now, if you just look at it and say, where would be the sharpest bend be? Well, logically speaking, it should be at 1, okay? And then it should have another one at -1, right? I mean, just if I were to guess, that would be the answer. However, it might not be. Now, the book gave a very odd answer, I think. So I did the calculations. Because the book says it's not 1, it's somewhere else. If it is somewhere else, like say if it's here, I don't know, the book gave a very odd answer. But anyway, let's say if it's here, okay? If the maximum curvature is here, then it should also be somewhere here, because this graph is symmetrical, right? Curvature just means how it bends. We don't care where. And this graph is symmetrical about 1 here, symmetrical by the y equal to x line. So then it should be another one here. And also, it should have 2 points where the kappa is at maximum. But anyway, so I did the calculation of kappa following the formula presented. And here's the formula, and I did the calculation, and then I figured out that kappa equals to this expression. Now at this point, theoretically, we can take the derivative, right, and set it to 0 and all that stuff and figure out when kappa is maximum. But I wasn't about to do that. So instead, I plotted into the computer to see where kappa is maximum. So I plotted this graph on decimals and then just identify where the maximum is. Okay, now look at this equation, right? I mean, see this? I mean, no way am I taking the derivative of this thing. Ugh. So, but if you just plot it out, the equation is obvious where the maximum is. As I said, the maximum should be 1 and -1, which, as you can see, decimals agree with me. The maximum of this graph, which is very beautiful. Look how nice it is. But anyway, the maximum is at 1 and -1. And that's the end of that problem. Next, let's look at problem 139. We have y to e equals to e to the power x. The question is, what does the curvature go when x goes to infinity? Does the curvature approach anything? So we will follow the formula of the curvature or something, and then let x go to infinity. And pulling some quick limit tricks, okay, here's the curvature, all right, and what happens when x goes to infinity? Well, theoretically, what happens is e to the 2x will get very, very big, right? So the 1 doesn't mean anything, so we can just ignore it. So if you ignore the 1, then the fraction kappa becomes the fraction of 1 over e to the power 2x, which then, of course, as x goes to infinity, this thing goes to 0. Now that's just a guess. In reality, what we're going to do is formally do the division, okay? And we'll divide e to the power x for both top and bottom and put it inside the parentheses. And so that's then you have to do some exponential, some algebra in the exponents, make it all come out, and you end up looking something like this, which one of them go to 0, the other one go to infinity, so together it goes to 0. And that's the end of that. Next, let's look at problem 141, which is 141 is more involved. What you're supposed to do is you're supposed to calculate the equation of the plane. Now, you're probably wondering, where do we do that again? And that's way back in page 195. So you look back on the page and refresh your memory. How do you do the plane? The plane is defined as n dot pq equal to 0, okay, and which is explained on the page, where n is the normal vector ABC and pq is the variable, where x minus x0, etc., where x0 and the initial point right here, the x0, is given to us and over here. So having done that, we are going to, let's see, so then after we've done that, then the next thing we're going to do is calculate the various things we need. What are we calculating here? We're going to figure out what the tangent vector is, okay? The equation, what plane are we doing? First, we are going to do the normal plane. The normal plane is defined as t dot pq. And so to do that, we need to figure out what t is, I guess, and do the dot product, and that will give us the equation like this. Okay, now based on the information we have, r of t is this, so we need to go by the definition of t. All right, and that's t, which is from, I don't know, previous section or something, and which is on page 275, but it's also on page 294. That's where I found it. Now, so anyway, so we know what t is, then we plug out what r prime is, and what is that? Is that r prime? Yeah, and divided by the normal, okay? For now, we don't care what the normal is, because we don't need a unit tangent vector. We just need the tangent vector, okay, no, regardless of how long it is. So we figure out what t prime is, I guess. Why are we figuring out the t prime here? Never mind, maybe we need it later. The point is, then we figure out t at pi. Well, anyway, right, t is calculated at pi, I suppose. In any case, the point is we have a specific value of t at that point. And at that point, then we do the dot product, ignoring the magnitude. Okay, it's dividing by something here, but we don't care. And then we are going to come up with, following the normal planes formula, and we come up with this equation, which turns out to be correct. Yeah, I should mention the reason I figure t of pi is because the original formula, where is the point is at t equals to pi. See, the y coordinate is t, right? So and where t equals to pi, so that's our original point. And then so that's why I calculate for t to come up with this. We don't need t prime right now, but we'll need it in a little bit. So I already figured that out here for, I don't know, no reason. Again, there's the actual magnitude over here is not important to us. So I didn't bother doing the rest of the math. We just need to know the vector part of t. Anyway, so then next so the normal plane is done. Next we need to calculate the osculating plane, same principle, except that we need to do figure out what the b is. Okay, now b is t cross n, so we need to figure out what n is. N is t prime, and which is what I did up here a bit earlier. Here's t prime, plugging in t equals to pi, I actually end up with 001, which is excellent. Because if you're going to do the cross product, you really want to cross it with something like 001. And that gives you a very quick answer that's probably right, because you're multiplying by a ton of zeros. So, so you get bailed out. And so then we have that as the answer. And then when you do the dot product, this is the answer. This comes out as the quick answer. Now you notice that the answer in the back is missing the y here, which doesn't make any sense. Okay, so just go ahead and put a y back, and then the answer is identical to what's written in the back. And that's the right answer, and also at the end of this section.